The next chapter is optimization models with integer variables. We've already seen some integer variables in the previous chapter where all we had to do is to enter a constraint for the changing cells to be set as an integer value. And once you do that, then Excel uses what is called a branch and bound procedure to find an integer solution for those variables. In this chapter, we're going to look at a more specific kind of integer variable, ones where the variable can only take two possible values, 0 or 1. These are called binary variables. And the solution procedure used is also branch and bound like previously. But once you set this requirement for variables to be a binary variable, then that allows us to model many specific type of problems which cannot be otherwise modeled. As we will see, we will look at 7 different examples of binary variable modeling. Okay, let's look at some basics. So a binary variable is one which is permitted to take either 0 or 1 as the possible value. So it cannot take any other value except 0 or 1. And so we can use this kind of variable to model whether a particular activity is chosen or not chosen, or particular activity is done, performed or not performed. So yes or no kind of decisions. So if the variable is equal to 1, then the activity is undertaken or a choice is made. And if it is equal to 0, that choice is not made or that activity is not undertaken. So that's how binary variables will work. Now, how do you solve a problem and restrict the variables to be only binary variables? So one possible approach is complete enumeration. That is, you look at all possible combinations of all the variables, each variable being 0 or 1, 0 or 1, 0 or 1. Now that will work if the problem is a really small problem. But if the problem is large, for example, say there are 100 binary changing cells, and 100 binary changing cells in practical terms is not that uncommon. It's quite regularly in companies will face problems with 100 or more binary variables, and in that case, if you do a complete enumeration, there is 2 to the power of 100 possible solutions to enumerate, and that's an extremely large number, and even a very fast computer will take enormous amount of time, days or even weeks, to solve a problem, and that is not practical. So we have to come up with a different kind of solution methodology which does not require complete enumeration, and we call that implicit enumeration. And one such technique is branch and bound. That's the most popular one, and that is what Solver uses to find solutions to integer programming problems in general, including the binary type that we are interested in this chapter. So what is branch and bound? So here, branching is a systematic way of taking one variable at a time and then setting the variable to the two possible values. Okay, suppose we have like 5 different binary variables. So you take the first one, set x sub 1 equal to 0, make that into a constraint. So that is your one problem here. And the rest of the variables you leave it as such. And then you have a second branch where you set x sub 1 equal to the other value. So if this was x sub 1 equal to 0, this one will be x sub 1 equal to 1. And all the other variables will not be restricted. Okay. You solve those two. Okay. And then from here, now that x sub 1 is forced to be equal to 0, now you take x sub 2 and put a constraint x sub 2 equal to 0 and make one problem there, that is one branch. And then so in that branch, x sub 1 will be 0, x sub 2 will be 0. Then you have another branch where you set x sub 2 equal to 1. So in this branch, you will have x sub 1 equal to 0, x sub 2 equal to 1. So you do the same thing on this side of the branching. So you keep branching, and you will have lots of different problems to solve. But that's only one part of it. If you just leave it like that, that would be complete enumeration. Now, to do implicit enumeration, you have to put bounds. Now, there are two kinds of bounds. There is a lower bound and an upper bound. So let's take the case of a maximization problem. In maximization problem, you want to maximize the objective function. So you come up with a lower bound and an upper bound. A lower bound would be a feasible solution, that is, all the variables conform to the 0, 1 requirement. And then you have an objective function value. Say the profit is $500. Okay. Now you know that the best possible solution cannot be any lower than this 500, because if you find a solution that's lower than 500, you'll throw that out and you'll use this one. So this forms a floor for your objective function value. So that is your lower bound, and that is also called incumbent solution. So that's a solution in hand. Now you're trying to figure out a better solution than this. So in any given branch, if you can find that the best possible solution going through that branch, okay, and that is your upper bound for that branch. What is the best possible solution that you can obtain going through that particular branch? And finding that is a little more difficult, but it can be done. So that's your upper bound. Upper bound is the maximum possible value that you can get branching through a given node. Now, if that upper bound is greater than this incumbent solution or the lower bound, then there is some opportunity to improve your solution, so you will keep branching. But if that upper bound is smaller than the lower bound that you already have, then there is no point in branching out through that branch. So you'll close that branch out and you will not do any more branching from that node. So this is what is called bounding. So you have branching and then you have bounding. So this way you can find the solution in a much faster time than complete enumeration. So if upper bound is less than, in the case of maximization problem, so it will be opposite. If it is a minimization problem, the whole thing will be opposite. So if upper bound is less than an incumbent solution in a lower bound, and you abandon that branch. So this is the procedure that solver adopts to find the best possible solution. Now when you run solver and you go into options, okay, when you go into options, you will see this screen. And here you need to understand a few things. We've already talked about constraint precision previously. So because there is a digital, this is a computerized program, and there is a fixed number of decimal places that the computers maintain. So you have a precision there. Automatic scaling, we've already talked about that. This is where you need to check, make sure that ignore integer constraint is not checked. Because if it is checked, then it will not give you all the binary constraints that you enter in solver will simply be ignored. Okay. And then this number here is very important, integer optimality percentage. Okay. So what this is what is called the tolerance setting. So what this means is that solver will, you have the upper bound for a maximization problem, right? Now if the solver finds the solution that is within that tolerance limit to the upper bound. So if you set 5% tolerance limit, once it reaches 5% of or 5% below the maximum upper bound, okay, what separates the current solution you have and the maximum possible value you could obtain is only 5%. Okay. Then solver will stop. It won't go any further. Of course, if you set it equal to 0, then it'll not stop until it finds the best possible solution. The reason why you want to set a non-zero integer optimality percentage is that to find that last bit of improvement, sometimes the solver will take enormous amount of time. And quite possibly the one that you have in hand is compared to the upper bound. So that upper bound may be unobtainable. Okay, what you have, even though you don't know for sure, what you have on hand is probably the best solution. So you want to put a non-zero number there, especially if you have a large problem. Of course, the problems that we will be working in this chapter, they're all small problems, so 0 optimality would be okay. But I think there are one or two problems where this may be an issue where you may want to put like 1% or 2%, something like that. So you will be able to stop once you know that you're pretty close to the best possible solution. Other solving limits that you can put is how the maximum time that you allow to go on, a number of iterations in the branching that you want to set a limit to. And these are evolutionary methods, so you don't have to really worry about these too. Now, there is if these are blank, there is an implicit default values. I think it is 100 seconds for time and 5,000 iterations, I think. I'm not 100% sure about that. But if in case that as you solve a problem, you hit the ceilings, you'll get an error message like this. So the maximum number of integer subproblems was reached. Do you want to continue anyway? So if you click continue, then it will continue until it finds the best solution. Or you can stop and leave it as is. Or you can go back to the options and set a larger number for the subproblem. And same here, maximum time limit. You can click continue if you want to continue, or you can click stop, or you can go back to the options and increase the time limits there, so this error message will not appear at that point. So we will now look at examples of 0-1 modeling, and there are 7 examples that we're going to look at, and we'll set them up as 0-1 modeling and solve the problems in Solver.